In this project, we are going to create an 8-bit divider. As you can see, AN goes through a multiplexer and goes to the ALU. The results passing through the D flip-flops also goes to the multiplexer. BN goes directly to the ALU, which cycles through a number of different flip-flops, interacts with the controller and a counter. We're going to build our circuit using Cadence or CAD Capture CIS. We're going to create a new project. Alright, we're going to be referring back and forth with the block diagram to place our parts and make our connections. So for the buffer, we're going to use a 74LS273 octal D flip-flop buffer. It contains D flip-flops, and on the clock pulse, it is going to pass those values through to the multiplexer. The multiplexer is going to be made out of two 74LS257 quad 2-to-1 multiplexers. The reason why we're using 2 is because one only supports 4 inputs, and we're using 8. The next thing we're dropping down is two 74LS382s. They are 4-bit ALU units. We're using 2 because we are doing arithmetic on two 8-bit values. We're going to use two 74LS93A counters. These are decade counters. Could also be used as a divide by 12 or a binary counter. This will serve as one of the inputs for another octal flip-flop. And will determine your quotient at the end of your arithmetic. You're going to place down a digital clock. We're going to edit the on and off times of the digital clock. We're going to set them both to 100 nanoseconds. Okay, now we're going to start making our connections. So first we're going to make all the A connections. So AN will be used by the stim 8 and as well correspond to all of the A inputs to the 74LS257s. And to show that these are in fact your A signals, we're just going to label the bus as well as its corresponding signals. The B inputs will be the outputs of your D flip-flop. We're going to tie pin 15 low, as well as connect the select A or B to a stimulus. And at 150 nanoseconds during the simulation, it's just going to default to high. Now we're just going to work on our B inputs. Similarly, since we're not going through a multiplexer, we're just going to plug in the stimulus and its corresponding signals to the inputs of the ALU. The outputs of the multiplexer will be the A inputs of the ALU. Now we're just going to start labeling our signals. If you refer to the spreadsheet for the 74LS382, if S0 is and S2 are low and S1 is high, you are using the subtraction function, and the arithmetic being performed will be A minus B. And since we're also performing subtraction, pin 15, which is carry in, will also be high. The carry out of the first ALU will be the carry in of the next. If you remember the block diagram, the outputs of the ALU will be the inputs of the D flip-flop. We're going to label our net F and do so with the signals. The same thing will be done on the other side for the inputs of the D flip-flop. We have to remember to make the clears high since they are active low. We also have to remember that the result of the multiplexer is also sent to another set of flip-flops, which will be the quotient, which will be the remainder of your arithmetic being performed. We take the output of the flip-flop and put it on a bus and label it RE to represent the remainder. One of the inputs of the AND gate will be your clock. This will help with determining when the clock is going to be stopped and sending the output register to keep track of the result. The outputs of this set of flip-flops will be your quotient. The carry out for this ALU will be inverted. So when the output is greater than 1, and the remainder is greater than the divisor, the clock will stop and send the output to the register and keep track of the result. This will also serve as the second input to the AND gate to determine when to stop the clock. So what we did there just now, we changed it to 4-4 so we would be able to write our values in hexadecimal for readability. So the first value for A will be FE. We're going to do the same for B, change the format to 4-4 to represent hexadecimal, and change this value to 0. After 50 nanoseconds, we're going to divide by 0f. Now it's time to run a simulation. We're going to create a new simulation profile and make sure that our settings are okay. We're going to change the runtime to 880 microseconds with a small step size. We want to make sure that we initialize all flip-flops to 0. Okay, so as you can see, A is FE, B is F, so when we divide the two, our result is 1/6 in hexadecimal, or 16, and the remainder is E. And we're just going to change these values again. Now A will be FF, and B will be 1. So FF divided by 1, you would expect to be FF. And that is the result, with a remainder of 0.